discrete probabilities. So with this one, they're going to be asking questions like the more technical questions, like sometimes without any stuff like this, or you're given a Venn diagram and you're asked to fill in some things, or it's not written as a Venn diagram, or you get stuff like independence, stroke dependent. Which one should you presume, independence or dependence? Yeah, you should presume dependence. If it hasn't mentioned it, just presume it's dependence. You can always use the combined events. Well, almost always use the combined events formula. You can't always use the independent events. You know, can't use this one unless it states that they are independent events. So like, what's the probability of getting heads and a 6 if you roll a dice and toss a coin? That you know that's they're independent events, so there's no chance of an overlap there. But if it's just a general one, presume that they are dependent unless they say that. If this is not true, also that's like a proof for dependence. If you want to prove that something is dependent and you have these two probabilities and it doesn't equal this, that's a proof. There's also mutually exclusive events. Yeah.
What was remember we had that one like question a couple weeks ago where we were like, show that it's independent or dependent, and then you got the same answer, like you got the
Yeah, so that's the probability if like B occurred. What's the probability of A occurring given that B is occurring? So you use the conditional probability one for that. So you can look back at that and you can ask me about it if you want. Yeah. So yeah, that's if one has occurred, given did it affect the A probability? Basically, if B occurred, did it affect it? That's what that one was about. And then mutually exclusive would kind of be like, if you have one roll of a dice, is it possible to get a 2 and a 5? You can't get a 2 and a 5 on one roll of a dice. You can only get, so that's mutually exclusive. It's impossible to get it. So there's no overlap with both those probabilities. So we'll look at an example question that in a little bit. With the tree diagram then, the main tricky tree diagrams is probably where you talk about conditional probability, which we'll talk about at the end. But they're probably a little bit simpler, but usually you start with your A or A leading into two events and so on, or whatever. There's two things, it's wet or dry, not A and B, A dash, and it leads to two events. We'll look at an example of that in a minute too, and the difficulty comes from conditional probability there. The difficulty here probably comes from like a misunderstanding because there's no context to the question. You don't know if you're right or wrong, and dependence and independent and combined all gets mixed up in your head. With anything with this, you know, practice is going to help. But yeah, hopefully that cleared that up a little bit, and we'll look at a question in a minute. With the other style, I would call these distribution questions. I think there's four main branches to this. There's like a discrete or a table version. There's binomial. There's a normal distribution. And then just a distribution function question. So, yeah, or which is called a probability density function, I suppose, to use its right terminology. So the table one is where you see something like less context again. You get x and the big X equal to x and the probability of one and the other, and you get 1, 2, 3, 4, 5, 6, and I'll just use rolling a dice. You get 1/6 here, 1/6 here, 1/6 here, 1/6 here, and so on, and that can be like a discrete probability distribution. So discrete means it's not going to be continuous data. It's just you get a 1 or a 2 or a 3. You don't get 1 point whatever. And then they might ask for quite often they ask for the expected value of this. So what would you do for the expected value of one of these things? You would multiply. So it's like, 1 can occur 1/6 times. So you do 1 times 1/6 plus 2 times 1/6 and so on. And then you get the expected value of, what's the expected value of rolling a dice? is 3.5, which of course you can't get, but it is the expected value of rolling a dice between a 3 and a 4.
Why do you do like 1 times 1 over 6 or 2 times?
Okay, so 1 occurs 1/6 of the time, 2 occurs 1/6 of the time. So heads, yeah, you can do it heads and tails. Heads occurs half the time, tails occurs half the time. Well, that doesn't work, is it? Because it's not numerical. Yeah, okay. Forget, but like, yeah, like let's say they're all going to equally likely occur. Yeah. But let's say they each had the value 1 through 6.
Yeah.
What's the most likely value to get?
Is on values.
Yeah. So the expected value is 3.5. Yeah. Okay. Then there's the binomial distribution. So these will all become a little bit more relevant when we look at the example, but it's about recognition now. Binomial distribution, you see X, distributed binomial. What's the two things here going to be in the bracket? N and P. What is N and P? Yeah, so trials and the probability of the one you want. Okay, so that's what you see in binomial. For that, to recognize a binomial, if it's not strictly said binomial, it quite often comes up in one of those long wordy questions. To recognize the binomial, you'll be looking for some sort of number of trials. Of the farmer has 200 tomatoes, what's the probability that some of them are underweight or something like that? So you're looking at, there's 200 tomatoes, 200 trials of tomatoes. You know the probability of a tomato being underweight. You start to apply binomial there. With our calculators then, we have a choice between PDF, binom, PDF, and CDF. What's the difference between those two again?
Cumulative is like continuous. It's like until.
Yeah. Think C for cumulative or continuous or more than one. PDF is one specific one where you want to go, right, how many times, like 6, you want 6 to happen. Whereas this one is 6 and back. 6, 0, 1, 2, 3, 4, 5, 6. This is far more likely that you'd be looking for X less than 6 or something like that. This is X equal to 6.
Does it include 6 when you see it?
Yeah. So if you wanted more than 6, if you wanted, let's say it was the other, let's do a different example. Let's say you wanted X greater than 7 on our calculator. You would do 1 minus X less than 6, wouldn't you? Because for our calculator, which not yours, Amos, but for our calculator, it only goes back to 0 for binomial distributions. Remember that. Only goes back to 0, so you'll have to work with the opposite if you're going up. But if you have a different calculator, it'll work out exactly what you want. And then normal distribution, we get X is distributed normally, and then in what goes in the bracket here?
0, 1.
It can be 0, 1. It's mean then, and it's actually variance or standard deviation squared. They generally don't confuse you too much with that. They will just tell you the mean and the standard deviation, but that's the way. If you see it, you're looking for this letter really to notice that it is normally distributed. Now, normal distribution is going to be probably the most common difficult question. One of the long questions is going to start with a normal distribution. And for that, I would always recommend drawing. Let's just come down here for normal. So our normal distribution is our old friend, the bell curve, which doesn't change. Never changes. That shape never changes. The mean is always perfectly in the center here. And then we know that it moves in standard deviations, one either side. Can you remember the percentage for one either side? Yeah, it's 68.2 each. Yes, I would definitely remember the first one, yeah.
What's the first one?
There's a 34.1% probability area here. So there's 68% chance that between what and what would I say this is here? Yeah, so this is -1 standard deviation, and this is +1 standard deviation. Of course, that would be using this symbol.
Are those just random numbers or actually?
These are the actual ones that always are. Always are. For any normally distributed thing, 68% of data lies one standard deviation either side of the mean. Always. And that's why, because that shape doesn't change and the standard deviation percentage never changes, that's why we can use z-scores. So it's about 99% outside of that. But we can use, this leads us to the z-score, which is a specific normal distribution where, I know I'm trying not to put it on my side, that in general, if the mean is what? 0, then one standard deviation plus one standard deviation, that we can get, if we know a number like the z-score is 2.3, we know that this has a massive probability of happening. It's 2.3 would be up here somewhere. We can actually get the probability of that from a z-score. Or work backwards. If we know a probability, because this shape never changes, we can work backwards and find what the mean or the actual standard deviation would be, because the shape never ever changes.
How can the mean be 0? I get that.
Well, you can just set it as 0. The mean of you, as in I suppose, you can think about it two ways. You can think about it as you've translated what you are dealing with to a mean of 0, like you've shifted the distribution to 0, or you can just think about it as this is the made up one, where a mean is something can have a mean of 0 in a probability distribution. If the mean is 0 and the standard deviation is 1, they have the exact same probabilities as all normal distributions, but this is the easiest one to deal with. Because as soon as I get a score here, I can get direct the standard deviation of all normal distributions. I can get all this, they're all the same shape, which means the probability of all standard deviations is the same. If something is one standard deviation above the mean in every probability distribution, it is at 84.1%, because I know it includes this 50 plus 34.1, no matter what the distribution.
So you kind of like start at, you start with the mean being 0 just to get the standard deviation, and then you apply that to, like, it's
Yes.
kind of like,
You separate it from the question you're looking at, and you go, this is what z-score is about. You separate, you just base it entirely on the shape of the distribution. And you're going, in general, what's the probability of that standard deviation?
so why does it bother adding the mean in the formula at all for you to assume it's 0?
Because we now link it back to the question. We link it back to the question. You find the mean, because we know in general the shape is the same. It helps us find the mean.
So is it kind of like u substitution?
What?
Not really. What you're thinking about is
Like u define.
when you got questions that they give you the probability, and they might give you either the standard deviation or the mean, and you have to work back to get what the other one is. What's the mean? We have the standard deviation, have the probability. How do I go back and find the mean? Or how do I find an x value given less just the standard deviation? Things like that. Here he is. So what you're thinking about is working back. If you don't have enough information to just type it into your calculator, you start to go, oh, inverse norm. What is the standard deviation of this probability? That's what inverse norm is about. If I have a probability, I can get the standard deviation from it, no matter what the probability is. So if you type into your calculator, if you go to inverse norm on your calculator, so clear this off, what have I got?
Wait, what does it give, the standard?
Inverse norm, you just put in an area into your calculator. It just gives you the probability. So if your area is, what area?
34.1.
If your area is 0.9, I put in 9. 0.9, what's 0.9 being? That's the area. When I put in inverse norm, so I put in the area as 0.9, and I put in the standard deviation as 0, or the mean is 0, and the standard deviation is 1. What does the score of 1.28 mean?
1.28 standard deviations away.
Where exactly away?
Like, yeah.
To the right, yeah. It's 1.28 standard deviations above the mean.
I don't get how that probability under the curve works at all.
Well, sometimes it'll tell you.
Well, that's going back to what I'm going to do next. The probability function will always have an area of 1, won't it?
So
Because
if you're going to the right and the mean 0, do you include everything on the left too?
yeah, all the way back, yeah.
So that
Unless
means
there's
in this
something.
case, it'd be a pretty high one because it's 1.28.
Yeah, 1.28 is above. Like remember, up to here, all the way back, is 84.1%. So if I have a 90% chance, that's up here, then it makes total sense. Remember, there is 84.1 because I include the 50% here and 34 here and a little bit more. That's about 90%. And that makes sense that the standard deviation would be 1.28 for that particular area. So if you know the area, you can always get the standard deviation by using inverse norm. And then from there on, you can start to use that z-score, it's called the z-score, to work out whatever is needed. Now, there's no particular example here to work with. We'll do a question towards the end where we need to work backwards. And then we got the probability density function, which you guys seem to be pretty good at because you love a bit of integration, which is you get a general function, which is not normally distributed, just a general probability function. And for that, in order to get the expected value, how do we get the expected value of a probability density function? You might know. X times the function, is it? Yeah, and from infinity down to negative infinity. Now, it'll never be from infinity to negative infinity because you'll always be given some bounds. It'll always be say this only works between 0 and 3 or something like that, and then that becomes 0 and 3, and then you do your integration for that with respect to x. So you're looking at, that's where it's just almost always probability density function questions have no context. It's hard to create context that a probability density function would only work between these two numbers, but would be continuous. It's quite difficult because most continuous probabilities are normally distributed. But you get something like this, and sometimes you have to. So this will give you the expected value. What else would they ask? Sometimes they ask for the median, don't they? So this will give you the mean. Sometimes they ask for the median. What do we do for the median again? We set it to 1/2, yeah. So it'd be different. But what do we set to 1/2? Equals. So we got m over here, and then you set to this to 1/2, and then solve for without the x, yeah. Okay. So let's look at some questions and see can we recognize what we would do. Mostly it'll be me going through because it'll take you a while to read it. And then we'll do some of the questions at the end. So let's look at some questions. So this first question, I got one of the other teachers to set up these questions in a random order to see what would happen just in an exam situation. So I haven't done these before, but I'm just reading it. Right, probability distribution. That is the table. I'm looking directly here at the table type 1. Find the value of Q. I think, all right, these have to add up to 1, and then to find
3 marks.
Yeah, to find the
No way.
to find the expected value, then this times this, this times this, this times this, this times this, add those answers together, we have an expected value. Right? Let's move on light work, as they say.
No reaction.
The time taken for a student to finish a task is normally distributed. Okay, so we're in normal distribution here. The mean and standard deviation is not given. Right, mean and standard deviation is not given. So for any sort of normal distribution question, I would draw. If it's not drawn already, I would draw. I think it gives you an idea of what you're looking at. So 6% of students take less than 7 minutes, and 75 take less than 22. So this is going, you're going to have to use some sort of z-score, inverse norm, because you have a probability, but you don't have the mean and the standard deviation. There's only one formula that gives me that. That's the x minus the mean over the standard deviation formula, which is the z-score formula. There's only one formula that's in. So 6% of students, so 6% would lie, I don't know the mean, but 6% is down here, isn't it? It's like here. So I know that this is my 6%, and that is 7 minutes. You can put in your area there, 0.06, maybe something like that.
So then is it 0.75 minus 0.06, and that's the area? 6%, and then you find 7.
Well, let's look. The other one is 75%. You can draw a second diagram, doesn't take that long. Take less than 22 minutes. Okay, so 22 minutes. Is 75% going to be above the mean?
To the right, but like in the middle of the
Do we think it's not going to be more than one? You can already predict the z-score, can't you? Z-score is going to be around what? Of 75%.
A bit less than 1.
Yeah, it's going to be 0 point something, isn't it? So here's, not 75, 22 minutes is up here. And this is 0.75, that area. Yes?
One standard deviation is 38%.
One standard deviation above the mean is going to be like 84%. Yeah. Okay, so what do?
I don't know.
I would like to know the z-scores. If I know the z-score, I can fill in this formula. I can put in z, and I can put in the x value. I go inverse norm, get the z-score of both, which I'll briefly do. Second, inverse norm,
0.67.
0.06 in general has a standard deviation of minus 1.55. This has a standard deviation of minus 1.55, or a z-score of minus 1.
Freaking, what are they called? Simultaneous.
Yes. And you'll get a z-score here as well, which we predicted would be...
0.67. We know it. It's 0.67.
It is 0.67. Oh, yes, 67. All right, Alex, calm down. Yeah, 0.67. So the z-score here is 0.67.
You hit it once for YouTube.
And now I can fill in this and what?
Standard, that's it.
No, I fill in this and my x value, the thing. So this is going to be, so I'll fill it in here for one of them. Minus 1.55 is equal to the 7. And now I still don't know the mean. And I still don't know the standard deviation. And then I do the other one, and then I simultaneous. Okay. All right. Well, it usually is, especially paper 1, yeah. All right, let's look at the next one, unseen. Time spent traveling to work by... Stop. Is distributed by a mean of and a variance. Okay, so we're given the mean this time. We're not given the standard deviation or variance. Probably we're given t is less than. Okay, this is once again. It's hard for me to visualize this. So I go yes,
Draw it.
Ryan. Yes, I did. Draw it. Yeah, just go straight to a diagram. I know that it's normal again. How do I know it's normal? Because they have said it. Probably won't spend as long on this one because I might give this one to you. This seems like a good one to give later. Okay, standard deviation. Find the probability between 30 and 46. I know the mean is right there at 45. So the mean
46.
is 45.
46.
Is it? Oh, 46. That's easier then.
Oh, jeez.
46. And I know the probability less. Oh, we can do this without a calculator. Less than 30. So less than 30, so let's just put 30 here. I know this area is 0.118. What is the probability between these two, isn't it? That's the first question.
So 50 minus that.
Yeah.
That's it.
Yep.
That's it.
But how did that come about? Maybe you would have if you'd done a number of these, but it took a diagram to make that super obvious.
Yeah,
That is just 0.5 take away, 0. Whatever that is, 3 some. Okay? Let's look through the question a little bit more. So find the standard deviation is back to probably z-score and stuff like that. Hence find the probability a random spends more than 60 minutes. So 60 minutes, that's going to be something back. I'm looking down here. A group of 12 employees is selected at random. A group of 12, what's that? Well, scream something to me.
Binomial.
It switches to binomial, yeah. 12 trials, and you know the probability of one of them. So it switches. And then, okay, that's going to be binomial of some sort, and then look at this. An employee selected at random spends less than 60 minutes traveling to work. Find the probability that their traveling time is between 30 and 46.
When we go back.
Now it switches to something else, which leads nicely to the last bit of the topic that I haven't. I'll share this presentation with you, but you might do it at the end of class today. But anyway, it switches to what?
To binomialspedia.
No, this is binomial.
Ah.
This is normal. And this is conditional. Now, we didn't speak much about conditional already, and that's why it can kind of come into anything. Not exact, this is not true that it's always applicable, but it could come into anything. Conditional probability.
Or just the given.
And that is when you see the word given, or something has occurred, what's the probability of something else occurred. Go to conditional probability, you see in your formula booklet, you can see there's one main formula, the probability of A given B, I think. It may be B given A, is probability of A intersection B all over the probability of B. Yeah? I'm right? Yeah. Okay, this is the main conditional probability formula. There is another one, Bayes' theorem, which is just a continuation of this, which I'll talk about in a second. So, yes, you have. We didn't, yeah, it looks horrible. They got, maybe I'll talk briefly about Bayes' theorem. This can be obviously rearranged whatever way you want, this formula. It happens a lot here where you have to rearrange it wherever you want. When it comes up here, it's generally the tricky part, or in tree diagrams, the tricky part is it'll be an application of Bayes' theorem where we go, right, Bayes is, I kind of need more space for this, so I'm going to,
You're going to write it out?
yeah, I'm going to write out one of them. I might just remove this, and then if you want, you can watch the video back later.
Okay.
Just talk about Bayes a little bit, and then we'll come back to our questions. So Bayes' theorem from the formula booklet is probability of B given A is probability of A given B all over the probability of B. Now, look at this formula while I write it out, and what is not in this formula?
What is what?
What's not in this formula compared to the...
Probability of A.
Yeah, that's not in this formula, but okay, anything else? The intersection is the thing I was talking about. Yeah. But yeah, you're right. You're also right. Probability of A is not there. So the probability of A intersection B is no longer here. And then there's let's get rid of the elephant in the room. The next stage in the formula booklet of the probability of B I given A and so on, which is a more complicated looking formula. The difference between these two formulas, this is, if you drew a tree diagram, this is the probability of A naught, and from then on there's only B and B naught. This one is used when it's A naught, and then there's more than one option for B. It won't go beyond 3, so it'll be like B1, B2, and B3. It's no longer just B and B naught. Does that make sense? So, if it's raining, they either take a car, bus, or cycle, or whatever like that. Or if it's not raining, car, bus, cycle. So that's when this one is used. You're probably far more likely to actually go back to this simple version of conditional probability, or an even simpler version of this, which I'll show you in a second. If this comes up, you probably are unlikely to use that formula because there's a simpler way of looking at this with a rearrangement of this formula. So let's look at that. This can be used for both these conditions, but I'll take the easier one. Now, if I relate this formula to this formula, what could this be written as? Let's say the numerator is the same. So the probability of that, what does the numerator mean? Can anyone explain what that means?
The given.
So what is this, yeah?
A given B.
The probability of B happening given...
Then A happens with B.
uh,
I got no idea.
The probability
Oh, that's
of
just,
B happening
that's just
given
probability
that
A
that's
intersection B.
hmm?
A intersection B.
Yeah.
A intersection B. See that? So that probability of A and B happening, given that B has happened, given that A has happened. But you can also do the same for the bottom of this formula. What's this probability?
A intersection B.
A intersection B.
Yeah.
Then plus.
Now it's not.
Intersection B.
Yes. Probably A intersection with a rearrangement of this. If B was B dash instead of B, that's also what this could be written as. Probability of A and B happening, and A and B not happening. This is the same application of this. Probability of A and B happening plus the probability of A and B not happening. Probability of A and B happening, the probability of A happening and B not happening. Because you want both probabilities to get the entire amount of probabilities. What that also could come down to, and that's exactly what Tease's question alludes to, what would this look like in a Venn diagram? The probability of A happening and B is this bit, yeah? And what's the probability of this? Where
That's just A. That's just A.
is this?
Yeah.
So what does this probability be? All ways that A can happen.
So why don't they just say probability? Oh yeah, you have to do that.
You come up with it from the tree diagram. How many ways can we get A? Well, you have to get these ones. You get this tree and this tree, and you add them together. Okay? So maybe that simplifies Bayes' theorem down, especially that second iteration of Bayes' theorem. If it was just three things, you just have to get all these probabilities and put them in the denominator.
So that the denominator is just probability of A.
Yes, but it can't always be found simply. You may have to go down. You may only be given conditionals and not A and B happening. That's why this is used. This is used most often, definitely. Probably 80% of the questions will just be straight up. You can figure it out. But this is just an application of this, because this then ends up being the exact same. We just said it a second ago. It's the exact same formula. It's just spread out.
But I don't remember that we ever actually used Bayes' theorem.
You did, but
Dude, I remember that one was on the
I always said you logic it out, and you don't think, so you logic out to find the probability of A using your tree diagram. I don't say, right, now we're going to apply Bayes' theorem nice and slowly and get each one of these. You just think about, all right, what's A and B happening? Yeah, we use this every time, but we didn't expand it. You expanded it in your head. You just think, oh, how can B happen? Oh, it happens this way and this way. They're the only two ways that B happens, and that's, you got it from the tree.
Technically, you don't actually need to use it.
No, so for most questions you don't even need to. It's not even in the question, but even for the Bayes' theorems questions, you can still come back to this and just think about every way that B can happen.
Yeah, that's just by drawing out
Yeah.
the tree diagram.
The only time it might come up is if they give a non-context example that they purely want you to use the formula to give you some condition, which is the very first type I looked at, where there's a Venn diagram, and you may have to do that, but that's going to be very rarely asked. Okay, so this is a good question to do. I'll share this presentation with you because it looks like we won't get many questions done today. Let's look at another unseen and see what we think. Oh, this is going to be shorter.
Oh, I don't want this.
So the probability of A. Oh, we can. It actually links very quickly to the last question, because how would I draw it? I'm going, the probability of A intersection B is 0.3. The probability of A intersection B dash is 0.3.
So A is 0.
So probability of A is
So the probability of A is 0.6. And you're ready thinking about that? Find the probability of B.
probably a formula.
Well, we know what they're independent events.
Independent, so then you just
So
0.6 equals probability of A times probability.
Yes, so you go straight to your formula booklet and then knock out that formula. Okay, let's move on. Continuous random variable.
Integration.
Yeah, you're straight to integration. It was the last type here, probability density function. You can see here this is exact 0 and 3. It's almost always something like this, 0 and 3 or 0 and 5, something like that. This piecewise function, is it confusing that they have it like this?
No.
Yeah?
Josh, you only look at like the x cubed. Right?
Yeah, you don't have to worry about the zero.
Yeah, you look at this and say, it's basically saying anything outside of this is nothing. We only look at a piece of the function, Now, piecewise can be a couple of functions together, but for all these probability density functions, it's only going to be one function. It's possible they could switch it into second. I haven't seen it, but let's go with usually, okay? And then you're going to do some sort of integration at this stage.
Is it ever going to be between infinity and negative infinity?
No.
No, because you can't do that, can you?
Well, I'm
Then in the
not
data booklet, it
Well,
should-
for
it should
normal
say-
distribution, it's between infinity and negative infinity technically, and there's like a proof of the limits of that, but we won't worry about that right now. Where does it switch at any stage? Is it just probability, normal probability density function? So median, you're talking about
12 independent.
going between m and 0.5, not m and 0 to equal 0.5 when you integrate. So you're talking about that. Variance, you're going to have to use x squared times the function, and then take it away from the mean. This strikes something to me.
Yeah.
That looks like binomial.
Yeah, it switches to binomial. It switches to binomial here. 12 observations. So you've worked out some sort of probability here, and now you have to apply that probability to a binomial. Next, that's another good one to do. I think we'll just do all probability questions tomorrow in class.
Like all of these.
Yeah, I think it's a good idea. Ideal would be if you have them done before we come in for any problems and questions. So I might just set that as homework. All right, biased coin is tossed 10 times at XP number of tails. What's the thoughts here? Biased coin tossed 10. What type is this?
So it's not 50%.
Yeah, that's one thing you know. It's not 50-50. It'd be pretty easy. What's your mind thinking? I'm thinking
Wait, don't
I'm
talk.
thinking binomial.
it's a binomial. Yes, a binomial distribution. Okay, probability of what's in terms of x. Oh, so that's you have to use these formulas for that. So there's binomial distribution formula.
What's inverse binomial? What? Is that a thing?
No, I'm not going to use that.
What are the two? What's the inverse? Is inverse PDF and inverse CDF a thing?
I think you're talking inverse norm. No.
Oh, it's like inverse norm.
For normal distributions, you don't use PDF, you only use CDF. PDF is doesn't make sense because you never get one. It's used sometimes in science and beyond, not in maths, because CDF is always because it's continuous, how do you find one particular point? P is think one particular point, CDF is cumulative. It has to be always cumulative for normal, otherwise we never get what's the probability of someone being 1 meter 73? Well, is it 1 meter 73 what? You can break that down. Where's the decimal point end? Yeah.
Wait, so the only inverse we
You're-
use is inverse normal, not inverse binomial?
Yeah, you don't use that. You want to use normal CDF, binomial PDF, binomial CDF, and inverse norm is your main friends. Eggplants.
What the heck is poison CDF? What's the one, bro?
Don't use Poisson either. Poisson is on. Well, of course. But you should already see this is normal distribution. Draw a diagram. It's going to switch. The longer questions almost always switch. What does it switch to?
Binomial. No, it's still normally.
Yeah.
It says eggplants are normally distributed.
Yeah, down here.
Antonio.
More than over a period of time has to.
Normal distribution.
Has-
Well, he has to reject 1 in 12 eggplants due to them being underweight.
Has to reject 1 in 12. So he's given the rejection. Okay, so 1 in 12 is rejected. Find the standard deviation. This strikes me as you may have to use z-scores here. Finding a standard deviation.
Just using the
I think
inverse
he's gonna post that on his
It might work, yeah. I haven't done the question yet, but just looking at it, I think there's going to be either a conditional here or a binomial here. So it's going to be binomial. As soon as you see the number of number of something someone brings, it's a trials. That's trials. Okay, I don't know if that might be the last question before you guys can start on these. Oh, another.
Goodness.
Jesus.
This
How
must be
many
different.
questions do you want us
Male
to do?
customer.
I don't want you to do any of them. It's up to you if you want to do them.
I'm gonna do all of them.
Yeah.
Veggie and chicken.
Yeah, veggie and chicky bird, ecus, and choose one of the following. Is this normal? Yeah.
0.65.
Wait.
No.
How is it normal?
I asked
Oh.
Trick question.
trick question. It's
Wants
not
to just say
definitely
yes to everything.
definitely not normal. I think this is like you would draw a Venn diagram here.
It's abnormal.
So you can only buy veggie, chicken, and both a veggie and a chicken. So that strikes me as I draw a Venn diagram. I could be wrong. I do see this coming up on a typical day, 600 customers, which tells me that could switch to binomial. And I also see, oh, this is nice. I would do this as a Venn. I would then switch here to binomial. And I can already see here, it is known that 44% of customers who come to the burger shop are females.
Normal.
I think this is conditional. Given, is there a customer is selected? Yeah, find the probability customer is female and buys chicken.
It's just tree.
You could use tree diagram. Yes, I would draw a tree diagram here, and I know it's conditional. I've used, it's going to be based here on, but you can just use conditional probability formula. All right. Let me share. Yeah, that's it. That's the last one. Let me share this presentation with you, and you can start in the questions. No points today, but we will do.